The next part in this linear programming graphical solutions for modeling with algorithms course is integer programming. Now, integer programming is the same as linear programming, except that one or more of the decision variables has to be an integer. So this is an extra constraint to the problem. So up until this point here for this linear program, we can see that there's no issues because this is just a linear program that we have looked at how to solve already. But now we have this additional constraint down here where x and y, they must be integers for this linear program. So for example, maybe x is making a number of something in particular and y is making a number of something else in particular, and having half or a piece of something made isn't useful, can't sell it or whatever the reason. We have this additional constraint, x and y are integers. So this video is not about solving a linear program, it's about looking particularly at the integer solutions to them. So I've gone ahead and graphed the feasible region. So in exactly the same way as we would solve a regular linear program, we take these 4 constraints and we graph them. This gives us this feasible region here. So all pairs of x and y now in this region are feasible. Except for this additional constraint now takes into effect. In the previous case where x and y were continuous, you could have any point in this 2-dimensional shape would give you a feasible solution. But now, because x and y are integers, our feasible region is actually now what's called a discrete feasible region. We have this point, this point, this point, the point under the R, this point, that point there, that point there, and that point there. And I would need to check if this one is 3, 3. 9 plus 30 is 39. So no, that 3, 3 is not in the feasible region. So the feasible region now actually only consists of these 1, 2, 3, 4, 5, 6, 7 pairs of x, y values. So we could look at all 7 of those and find the optimal solution because it is just a finite number of them. But when you've got more complicated problems with hundreds of pairs of x and y values, that's not really very efficient, and that's not what the exam expects you to do. So let's go through and have a look at what the exam would expect you to do. So we ignore this constraint to start with. We just solve this linear program as we would normally. So I've got the 4 vertices of the feasible region, A, B, C, and D, and we're going to have, I'm going to find those points, and then we're going to plug those points into the objective function and see which one is maximized. So I've not done this in any of the videos for linear programming yet, but I thought I would do it here so we can see using the calculator to solve them, just in case you haven't checked out my video on solving simultaneous equations. So what I've done is I've gone into equation mode. This is a mode that is on the FX series as well, not just the graphicals. It's a simultaneous equation because I'm looking for a point of intersection. It will only do linear lines, but that's fine in this case. We've got 2 variables, x and y, and then it's got this anx plus bny plus equals cn, and it's got the 2 equations there. So, for example, if I want to find the point A, I'm going to look for the intersection of this line, which is y equals x. So that's 1x minus a y equals 0, and the equation of this line, which is 3x plus 10 equals 40. So I'm going to do 3x plus 10 equals 40. And this is now the point A. Okay, so 3.1, 3.1. It's actually 40/13, so I'm going to keep it exact. Okay, and then I do the same thing for point B. Now point B, rather than clearing everything, it's still on this line, so I'm just going to replace this bottom equation. Because it now lies on this one, which is 2x plus 5y equals 30. So 2x plus 5y equals 30, and that's going to give me 30/7. So 30 over 7, 30 over 7. And then point C, well, x is 8 because it lies on that line anyway. And then it's going to lie on this line. So if I plug in x is 8 into there, I get 16. So 5y must be 14. So y must be... 2.8. And then the point D down here, again, x is 8 because it lies on this vertical line. Plug in x is 8 into there, I get 24. So therefore 10y must be 16, so y is 1.6. Okay, So those are my 4 points. Now I take those 4 pairs of values for x and y and I plug them into the objective up there. So I'm going to go back into computation mode on my calculator. So menu number 1. Right, 4 times x, that's 4 times 40/13 plus 7 times y, which is 7 times 40/13. And that's going to give me 440/13 or 33.8. And I'll repeat that process for the other points. So that's 4 times 37ths plus 7 times 37ths is 47.1. And then 4 times 8, let's do a different line, 4 times 8 plus 7 times 2.8 is 51.6. And then 1.6 there instead. It's 43.2. Okay. So that gives me the 4 values of P, and I can select then that this one is the maximum. The problem is that, yes, x is an integer, but y is not. So although this is the optimal solution for the continuous linear program, it is not the optimal solution for this discrete linear program. So what I do next is I'm going to zoom in at this point, C, and I'm going to look at all the integer points around it. So let's consider, first of all, the point C1, which to get C1, what I'm going to do is I'm going to round both of these down to the nearest integer. And I know that 8 will round to 8, but I'm actually going to put 7, just in case rounding that down to 7 and then pushing that up past 7, past 3, sorry, is a better solution. So I'm going to round them both down to the nearest integer, but not subtracting more than 1. So that's going to be the point 7,2. So that's here on my graph, 7,2. So that's in the feasible region. And if I plug 7,2 into the objective function, I'm going to get 4 times 7, which is 28, plus 14. So 28 plus 14 is 42. Okay, now I'm going to look at, can I increase x? So the point C2, 8,2. Well, we know that's in the feasible region, but you should just check it against all of the constraints. 8,2 does satisfy all of the constraints, because if I plug in 8,2 into here, it is greater than 40, and it does satisfy this. So if I plug in 8,2, I'm going to get 4 times 8, which is 32, plus 14, which is 46. C3 then, so keep increasing x, 9,2, that might be in the feasible region, but we can see that actually it's not, because it doesn't satisfy this inequality, so I reject it. Now, go back to this one, and instead of increasing x, I'm going to start to increase y, because I might find a better solution by increasing y instead, which is why I came back to 7,2. So if I check 7,3 now, let's see if that's in the feasible region. It is. And you can check it against this constraint here. So 14 plus 15 is 29, which is less than 30, so it's satisfied. So 7 in here, 4 times 7 is 28, plus 21 is 49. So 49 goes there. And then try it again. Increase y a second time, 7, 4. And just check it against all of the constraints, and we'll find quite quickly that it does not satisfy this constraint. Okay, so I'll plug in 7, 4 into there. I'll be doing 14 plus 20, which is 34, which is not less than 30. So therefore, that is not in a feasible region. Easy to spot on this graph because the numbers are quite small. But when you've got a more complicated problem, it's not as easy to spot. So it is worth just running these through the algebra. Okay, so that gives us all of those. And now we choose the biggest, and that is that one there. So the solution to this linear program is the maximum value of P is equal to 49, and that occurs when x equals 7 and y equals 3. Okay, there we go. Now, an interesting feature with integer programming is that we did make an assumption in all of this process, and our assumption was that we assumed the linear program, the integer programming solution, was near the linear programming solution. So that is not necessarily true. Okay, now it is true in this case. It's quite easy to prove because there's only 7 points. We can just run them all through, and it will come out that this one is indeed the best. But we can't prove that here. Well, I'm not going to prove that here, rather. But what I'm going to do is I'm going to look at a slightly different linear program where it is disproved. So, for example, it looks to be the same program, except I've just replaced 4x plus 7y with 4x plus 9y. All of the constraints are exactly the same. So we've here what I've done is I've run through the numbers again. I've selected the point C, which again was the optimal solution for the linear programming continuous equivalent problem. And I've then run through solutions which are near it. And I came to the conclusion that 8.3 was, 7.3 was optimal, which is when P is 55, and that's X is 7 and Y is 3. Okay, so very similar to the setup I had here, except just with a different objective function. But in this case, let's do this in red. Let's consider the point 5.4, which is here. Now that is in the feasible region, quite easy to see. We only need to check it against one of the constraints, which is this one, just to make sure that it is inside. So the 0.54, that's going to be 10 plus 20 is 30, so it lies on the boundary, so it does satisfy the constraint, so it is in the feasible region. This point implies that P, I'm going to get 20 plus 36, that's 56. So even though C was the point which was the optimal solution for the continuous equivalent of the linear program, the discrete solution is actually all the way over here close to point B. All right. Now for the examination, you do not need to jump from a vertex to another vertex for the integer programming problem. You just need to be aware that the optimal solution to the integer linear programming problem is not necessarily near the optimal solution to the continuous equivalent. Okay, so just make sure you're keeping those, keeping that idea in your mind when you're solving this. So this is not necessarily optimal anymore. One could argue that this is a heuristic algorithm. It doesn't always give the optimal solution, but it gives a good one. Okay, this is good. We've only lost 1 point from 55 to 56. So it is a good solution, but it doesn't guarantee you find the optimal solution. Okay, so that's example number 1. Example number 2, this one is quite a bit more complicated because of the numbers that are involved. And I wanted to show you this one because you can't just keep looking at the graph to see the what's called the lattice points, the integer points. Is because there's too many of them. So we've got this objective function, 9x plus 4y. We've got 1, 2, 3, 4 constraints. We've got the extra constraint now that x and y must be integers. So it's an integer programming problem. And we've got this feasible region here. So I've drawn it all out, and now we're going to have a look at solving these points. So A, B, C, and D. A is the intersect of this line and this line. So again, let's just have a look at doing a couple of these on here, and then I'll perhaps write the others down. So again, simultaneous equations with 2 unknowns. I'm going to delete everything that's in there. Okay, so to the point A, I'm looking for intersection of y equals 4x and 2y equals x plus 100. So y equals 4x, what's going to be 4x minus 1y is 0, because you've got to get the x's and the y's on the same side of the equation for this mode. And then this equation, we're going to have perhaps negative 1x plus 2y equals 100. So the point A is 14.26 and 57.12. So I'm going to jot that down here. So I'm going to put the exact numbers. So it's at 100 sevenths and 400 sevenths. Okay, and I can do the same thing for B, C, and D. So let's just run B. Now to do B, it's already on the line y equals 4x, so I don't need to put that in again. and I'm going to get 20x plus 10y is 395. Oh, sorry, no, 3951 even. So I get 65, or 1,317 over 20, which is exactly 65.85. Nice rational point there. That's finite decimal. 363.4 there. And then the point C, got decimals for that again. So 104.8, 185.5. And then the point D was 132.5 and 116.25. And those last three, they're exact. They're not rounded. Okay, so now I've got those values, I'm going to plug them into my objective function, which is up here, to give me my values of my objective variable. So 9 times 100/7 plus 4 times 400/7 is 357.1. And then 9 times 65.85 plus 4 times 363.4 is 2046.25. 9 times 104.8 plus 4 times 185.5 is 1685.2. And the final one is 1657.5. Okay, so out of these, oh, hold on, that is not the right answer for that one. Let's try that one again. How did I get that? 9 times 65.85. Oh, that's because that's not the right coordinate. Now it's 263. Apologies. That should be 263.4. So that's 1646.25. There we go. Okay, so looking at these four values now for P, we choose the biggest, which is this one. So that would be the solution to the continuous linear programming problem. But we've got this extra constraint where x and y are integers. So what I'm going to do is I'm just going to round both of those down to the nearest integer. I'm going to call that the point C1. Okay. So that's going to go to 104 and that's going to go to 185. So 104, 185. Because from the point C I've gone down and left, I'm guaranteed to be in the feasible region. So I know that that is a feasible solution. And what I'm going to do is I'm just going to compare all the integer points with the two constraints that C is associated with. So that is going to be this one here, which is 20x plus 10y, and that needs to be less than or equal to 3,951. And then I've also got this constraint up here, which is 5x plus 2y is less than or equal to 895. So I'm just going to check if these points lie in the feasible region. Okay, so the first one, 20 times 104 plus 10 times 185, that is 3,930, which is less than 3,951, so that is satisfied. Okay, the point C2, what I'm going to do is add 1 to the x. I'm going to be moving to the left, so that's 105, 185, and just run that through again. So adding 1 to the x is going to add 20 to this side, so it's going to be 3,950. Again, that is satisfied. Check the other one. So 5 times 104 plus 2 times 185. That is 890. That is satisfied. So therefore, because both of these constraints are satisfied, it is in the feasible region. Adding 1 to x is going to add 5 to that, so that's 895. Again, that is satisfied. But as soon as I add the next one, that's 106, 185. That's going to add 20 to this one, which is 3970. So that's now left the feasible region, and that one has actually as well. Okay, you need them both to be in the feasible region, both inequalities to be satisfied to be in the feasible region. So I'm going to reject C3. So now I go back to C1, and instead of increasing x, I'm going to increase y. So keep x fixed at 104, and that's going to be 186. Let's check to see if this is in the feasible region. So we're going to have 20 times 104 plus 10 times 186. In fact, I didn't need to do that because I'm just adding 10 to these. So that's 3940, that is satisfied. And here I've added a y to that, so I'm only going to add a y to that, which is going to add 2, so that's 892, so that's satisfied. 104, 187, again add another 10, so that's 3950, add another 2, so that's 894, they're both satisfied again. Check C6, which is 104, 188, that is 3960, which has now left the feasible region, so I don't care about that one, I can ignore it. Right, so now I've got these points, I'm just going to check this one and this one. Okay, so that's locking y and maximizing x, find a value for p for that. And this is locking x and maximizing y, and let's find a maximum value for that. So if I plug that through, that comes out to be 1,676. Okay, so that's me plugging this point into the objective function. And then I can do the same thing to this point, which comes out to be 1,684. Okay, so these are my two options now. Choose one of those two. This is the biggest. So that's the one I'm going to go, oh, hold on. 105, 185. No, that's not right. That is 1,685. So this is the one I'm going to go with. Sorry, I looked at the wrong number on my sheet. Yeah, so if I plug in x is 105 and y is 185, I get p is 1685. Whereas at this point, I get p is 1684. So this one is bigger. So therefore, the maximum value of p is the 1685, and that occurs when x is 105 and y is 185. Okay, that may or may not be the optimal solution because this is heuristic at this point. However, I do know it's optimal because at C it was 1,685.2. So the absolute maximum it can be if x and y are both integers. Okay, if x and y are both integers, then p is an integer. The absolute maximum it can be is 1685. It can't be more than that because x and y are integers. And because I found one that's 1685, then that means that must be optimal. Okay. Doesn't mean the converse is true, of course. If this wasn't the integer below this value, then it doesn't mean it's not optimal, because it could still be optimal. All right. I know there's quite a lot in this video. I hope it's been okay. But again, if you have any questions, as usual, just drop them in the comments below. But that is integer programming. Hope that all made sense. Thanks very much for watching.